My name is Thomas Bayer, and I'm your moderator for today. Along with me, we have our technical experts, Eric Goebbels and Peter Eibeck from product development, and Ingvar Henning from our research team. The experts will answer your questions in the Q&A session after the presentation. Please be aware that throughout the webinar, you will be kept muted, so please use the chat function to forward your questions to us. We will take them up after the presentation in the already mentioned Q&A session. I think all is set and we're good to go. So Eric Goebbels will guide you through the presentation, and I will now hand over to Eric. Eric, the stage is yours.
Thank you, Thomas, and a warm welcome to all attendees of this webinar concerning the new Ultradur RX portfolio for high-performance radar sensors. Thank you for showing interest in this topic and in this new Ultradur material class. And today we will present you with 3 new Ultradur-based compounds designed specifically for the absorption of electromagnetic waves. Before we dive into the materials, just a brief introduction. And as many of you know, radar sensors are one of the key sensors for the advanced driver assistance systems. And current examples of these obviously are adaptive cruise control, anti-collision warning systems, and the automatic brake assistance. However, in the future, with more and more cars getting radar sensors, and also the amount of radar sensors per car increasing, this means that the amount of electromagnetic radiation on the roads will increase. And this obviously also poses a challenge, because for the optimal working of such sensors, the interference of electromagnetic noise, maybe it from another car, is prohibitive. Therefore, we have designed these materials to hopefully solve this challenge and enabling the optimal working of radar sensors also in the future. Here is an overview of the Ultradur RX product portfolio, RX standing for radiation extinction. There are 3 materials in this portfolio. First of all, the B4300G4 RX1, meaning the first generation radar absorber, RX1. Then secondly, the B4340ZG4 RX2, and the RX2 here indicates as the second generation material. At the end, there is the Ultradur B4520 RX2. Even though all these materials are good absorbers for electromagnetic waves, these do have, let's say, the lowest wall thickness for optimal absorption. And as you can see, this optimal wall thickness decreases from the first generation 3 millimeters to 2 and 1 millimeters in the second generation. These materials also have other features. For example, the first material, the B43G4 RX1, and the second material, both are reinforced with 28% of glass fiber, and the second material also is impact modified, giving these both materials very good mechanical properties. Therefore, we feel that these 2 materials could be very well suited for housing applications or for parts where higher mechanical loading of the part is to be expected. This final material, as you can see, is unreinforced. This material has been designed specifically for very high electromagnetic wave absorption, especially at low thicknesses, as you can see from the 1 millimeter. However, obviously this changes the mechanical properties of such a material because it's not reinforced. Therefore, we feel that these materials or this material is more suited for inserts for local radar absorption inside a radar sensor, for example, or for parts with lower mechanical loading, where lower mechanical loading can be expected. Nevertheless, the absorption is something which depends on the material thickness, which we'll come back to in a few seconds. And as such, the right material needs to be found for each individual application, which one could consider. Before we show you some of the performance of which these materials can bring, we would like to talk briefly about the interaction of electromagnetic radiation with condensed matter. As you can see in this graph, the orange bar here represents an absorber, and this gray wave curve or sinus-shaped curve shows an incoming electromagnetic wave where the incoming power is denoted as Pn. The wave hits the material on the front surface, and there a part of the wave power gets reflected, denoted here as R1. And this reflection is governed by the dielectric permittivity of the material. The relationship is, the higher the dielectric permittivity, the higher the reflection R1 of the front surface will be. If we stick to the point of reflection for a second, the reflection is also governed by the thickness of the material. As you can see, the second step in a dielectric permittivity change between the material and air is at the backside of the material, so also part of the radiation is reflected from this end. And obviously, the scheme is simplified for this moment. The thickness can have both directions. Increasing the thickness of your material can lead to high reflection or lower reflection, depending on if it's a constructive or destructive interference. And I will come to that on the next slide. The next point is the absorption, for what an absorber is there. The absorption of a material is governed by the dielectric loss of a material, where the rule holds, the higher the dielectric loss, the higher the absorption. Polymers themselves generally have a very low dielectric loss and therefore cannot efficiently absorb this electromagnetic radiation. Therefore, particular additives need to be added to ensure proper absorption. Typically, dielectric permittivity and dielectric loss cannot be tuned independently of one another, so the optimum in both needs to be found. Also, the thickness plays a role on the absorption, where typically one can say that if you increase the thickness of an absorber, the absorption will also increase. However, this is not always the case. At the end, there is still the transmission left, and the transmission is nothing more than 100% of the incoming power minus the reflected power minus the absorbed power, and here is denoted as PT. We briefly mentioned the thickness dependence of absorption and this interference pattern, which can be obtained depending on the thickness. And this we want to elaborate a bit further for you. Here you see a simulation of a material. It is an Ultradur B4300G4 uncolored, which is not an absorbent material, but more suitable, for example, for a transmittant material, which has a dielectric permittivity of 3.2 and a dielectric loss of 0.04, which is very, very low. And as we'll show later, this is not an efficient absorber, therefore. One can immediately see a very dependent behavior based on the frequency and the thickness of the material. And this is this constructive or destructive interference pattern I spoke of on the last slide. If we have a look on one frequency, we've chosen 75 gigahertz, but you can choose any frequency within this range. And you can see that even within this frequency, there are 3 points or 3 thicknesses where there is destructive interference, and there are 3 points where there's constructive interference, showing this thickness dependency, which can go both ways. This is for a non-absorber. For an absorber, this behavior is less pronounced. However, it's still there, and therefore we decided to show you this behavior in one of its more extreme forms for you to understand that in all types of materials, such a behavior can occur, and therefore the thickness needs to be, let's say, thought about carefully. If we then look on one thickness and then frequency dependent, you see a similar behavior, although there's only one minimum and one maximum. However, it can be said that depending on the dielectric parameters of a material, but also depending on the thickness, as we just showed you, there can be a very pronounced interference pattern, which needs to be considered. Now let's move on to the Ultradur RX materials and their performance. Here you can see the 3 materials I've just introduced to you at their optimal thickness measured at 79 gigahertz. So 3 millimeters B4300G4 RX1, 2 millimeters B4340Z G4RX2 and the unreinforced B4520RX2. The first noticeable result is that all materials at their optimal thickness are strong absorbers, absorbing almost 80% of the incoming power. Reflection was found to be between 15 and 20%, depending on the material, and the transmission generally below 10%, for some materials even below 5%, showing materials can absorb a large amount of the incoming radiation. If we look onto the decibel values, the absorption in decibels, for example, for the B4300G4RX1 material here in blue is 10 decibels. This means that the material reduces the power of the incoming of the electromagnetic wave which enters the material. And when I say which enter the material, it means the total energy minus the reflected part, because this doesn't enter the material. So the total entered power gets reduced by a factor 10 by this absorber. In the case of this sample, even by a factor 100, so 20 decibels. If we then consider the thickness of these materials and we calculate the specific absorption, so decibels per millimeter, we see a clear difference where the first generation absorber is approximately 3.5 decibels per millimeter. And in the second generation absorbers, you can see 10, 11 decibels per millimeter, showing that these are very strong absorbers, especially this one at lower sample thickness. Considering the dielectric properties of such Ultradur RX materials, again at 79 gigahertz and optimal thickness, a few things can be noted. We talked about, or we showed, the B4300G4 uncolored, so the non-absorber in our interference example, which had a dielectric constant of 3.2, around here, and a dielectric loss of 0.04. Let's first talk about the loss, because the loss makes an absorber great. You can see that already for the first generation absorber, we reach a dielectric loss value of 1, and the second generation even reaches values around 3, showing their capability of being absorbers. The dielectric constant increases to about 5.8 or around 5 for the second generation materials, showing that they're not too high to create a very high reflection, which would happen if you increase the dielectric permittivity too much. However, it is interesting to note, as I mentioned before, the dielectric permittivity and loss cannot be tuned independently of one another. However, we were able to reduce the dielectric permittivity, but significantly increase the dielectric losses, making the absorbers a material which reflect not too much radiation, but absorb most of it, which is also addressed by the Tangens delta, which is nothing more than the quotient between the dielectric loss and the dielectric permittivity. We brought one example for the thickness dependency of a material, for the B4520RX2. Again at 79 gigahertz, but this time at various thicknesses ranging from 1 to 3 millimeters. One can see that actually the absorption remains relatively constant, and there is only a small change in the reflection, where it's increased if you go from 1 to 2 millimeters, because at 1 millimeter there is this destructive interference occurring, therefore the transmission is a bit higher, but reflection is lower. Also here we consider the decibel values, and this actually gives a very homogeneous picture if you consider the thickness. The specific absorption which we look to for let's say these various thicknesses remain somewhere between 11.5 and 13 decibels per millimeter, showing that this material has a very constant absorption over a very wide range of thicknesses. These Ultradur RX grades were developed in a close collaboration between our material development department, our analytical department, and physical modeling. Especially also here, our analytics department has the capability, but also the analytical equipment to analyze materials at these high frequencies, for example, between 60 and 90 gigahertz, and also a whole bandwidth of materials can be analyzed there, from absorbers to transparent materials. We feel that because of our expertise in all 3 of these areas, we as BASF are a good partner for your radar absorbing solutions, and Ultradur RX portfolio might be the key to that. From all materials shown in this webinar today, there is sampling material available. And if you have interest or you want to have more information, please contact Thomas Beil, this email address, or visit our website, which the URL is shown over here. And with this, I would like to thank you for your attention, and I give the word back to Thomas Beil.
Yeah, thanks, Eric, for the presentation. We're going over now to the Q&A session. So please post your questions via the chat function. And I also already see that we have already received some questions. Maybe we'll start with a question directly for you, Eric, because you need to clarify something on slide 7. We received a question, are you talking about thickness in millimeter, or you're talking about micron thickness? So if you can go back to slide 7, that's where this question appeared. Maybe you can state which thickness you are talking about, millimeter or micron thickness.
These thicknesses are all in millimeters. So all the samples are listed here in millimeters, 3 millimeter, 2 and 1 millimeter respectively.
All right, thank you. Then the next question which arrived, are these materials exclusively for radar applications, or are they also beneficial for LiDAR applications as well?
Yeah, me try to answer this. So for a LiDAR, we have a completely different frequency range. So LiDAR usually is in the near infrared range. So the wavelengths are in a several hundred nanometer range, and the radar radiation, what we are talking here about, is in the millimeter range. So therefore, all the benefits that the RX materials show for the radar frequency cannot directly transfer to the LiDAR technology. So then we would need new and other materials which specifically would target these higher wavelengths that comes along with the LiDARs.
Okay, thank you. Then the next question would be, what kind of measurement setup is available within BASF? Maybe this is a question for Ingolf.
Yeah. Our setup in the physics department consists of a vectorial network analyzer with wave extenders, and a sample holder is a so-called corrugated waveguide from Swiss company Swiss 212. The whole equipment works in the range 60 to 90 gigahertz, so we can make easily frequency scans. We measure the transmission and the reflection coefficients of the sample inserted in this corrugated waveguides. And from these measured so-called scattering parameters, we can calculate the dielectric parameters of our investigated material. Yeah.
All right. Thank you. Then the question about availability of sampling material. Maybe that would be something for Eric to show it on the slide again. So sampling material of all shown grades are available, and also there arrived the question about availability of these new grades within and outside the EU. And just to give a statement here, in general, it's possible to sample the materials outside of Germany, but from the German government, these materials have been classified as so-called dual-use goods, and they need an export approval from the German Federal Office of Export Controls. But in general, this is just some documents which need to be filled, and we have to apply for this export license together with you. So then I received another question or statement, very good performance at 79 gigahertz. How is the performance over frequency from 76 to 81 gigahertz?
Yeah, I can answer this. There is no significant frequency dependence in this frequency range, automotive range, meaning the dielectric parameters are more or less frequency independent, and also the scattering parameters, they are more or less frequency independent. There are only very slight changes in the range of a few percent.
Okay, thank you. Then I received a question about laser weldability. So is laser welding possible, or other welding technologies which have been already tested yet?
Yeah, let me comment on this. So welding in general is possible. Those materials are standard thermoplastic materials, and this means that several welding techniques can be applied. For laser welding, there is a specific need to have also one laser transparent mating partner, and these materials cannot act as a laser transmittive welding partner. So as a laser absorbent welding partner, that is okay. But for laser transmission, other materials are needed.
All right, thank you. Then there was a question about electromagnetic radiation. So can these materials be used for absorbing electromagnetic radiation, also for wireless charging applications? So when you're talking about EMI shielding, maybe this would be something for Ingolf.
Yeah, I can make a comment. So going to much lower frequencies, below 1 gigahertz, therefore the materials are not optimally designed, because the dielectric permittivity will increase towards lower frequencies. This will cause a higher reflection, and therefore the absorption will get a little bit lower. So they are not optimally designed for this frequency range, but one could do this.
All right, thank you. Then again, a question regarding the sampling. For sampling purposes, also plates available or only pellets? I think this can be answered quite quickly. Who wants to go?
Can answer this. Both sample forms can be obtained. Plates can be injection molded and sent, and we can also sample granulate.
Okay, maybe then you can also take the next question. Is this a material for injection molding, or is it only available as plates?
This material has been designed for injection molding in various shapes. So three-dimensional shapes. So housings, for example, can be made from this material. For sampling purposes, plates are obviously a bit easier. But in general, this material is for injection molding purposes.
All right. Then there was a question about temperature increase by absorbing. So maybe we have to explain again how the absorbing properties are generated. And maybe that would be a question to Inge. So what is the physical mechanism behind the absorption, and is there a temperature increase measurable?
So our materials, the absorption is created, let's say, by the dielectric loss of our materials. We have really dielectrics, so we have no conducting materials, because conductivity would increase the reflection. And the dielectric loss that determines the size of the absorption, this loss is, let's say, created by a so-called interfacial polarization mechanism in our heterogeneous material. And we have done studies of the absorption and of the dielectric parameters up to in the range of 120 degrees Celsius. And because this is a special interfacial polarization mechanism, nothing significant happens to the dielectric parameters up to this temperature range. That means they are more or less independent of the temperature up to this range. Yeah.
Okay. Thank you. I hope this makes it a bit clearer. Then a question which is quite general: where can I find technical data sheets for these materials? I think that is quite easy to answer. You will find more information. Yeah, thank you, Eric. If you switch to the slide again, you'll find more information on our website. Or you can directly ask me, and interact with me and ask me about more details. So there are quite some questions coming in. Then there's a question about Ultradur material in radar housing. So what is the difference to already existing materials which find their way into radar housings? And what is the specific difference here with these Ultradur RX grades? Maybe Peter?
Yeah, sure. So the existing Ultradur grades in general are not absorbing materials, and they are in this wave length range. They are more or less behave like transparent materials, even if they are colored black. So all what is currently in the market is not an absorber for this type of radiation.
Maybe you can also comment on the other materials which we have in our portfolio for radar sensors. Maybe just to bring it to the mind, the community.
Yeah, of course. So beyond of these new developed RX grades, we have several other materials that are in general for use in automotive E&E applications, for example, also in radars, in the manufacturing of radar sensors. So when you manufacture housings, for example, then we have ultra-mid or ultra-dur materials with reinforcement, with hydrolysis resistant additives, but also for laser transmission welding. We have laser transparent materials. So there is a big variety of materials that can be used in radar sensors or more general in automotive E&E applications. But all these older materials or existing materials are not absorbers for this radar radiation.
All right, thank you. So I would say we just take two more questions before closing the session. One question maybe to Ingolf. Do we have tests with incident angle dependence?
So in our apparatus here in our lab, we measure only the normal incidence behavior, but we have done measurements on our materials together with external partners, and we measured the incidence angle dependence of the scattering parameters and also of the dielectric parameters. And the main message is that the dielectric parameters of our material in the incident angle range from plus to minus 50 degree is independent of the incident angle, and that means you can simply use simulation programs based on the Snellius equations for refraction and calculate the scattering parameters. Yeah, so this is the main message. The dielectric parameters are independent on the incident angle in this range from plus to minus 50. The scattering parameters, of course, will depend on the incident angle.
Okay, maybe the last question is also for you. If the energy is not converted to heat, where's the energy going?
Oh, of course, the energy that is absorbed is converted to heat. That is the mechanism of the dielectric loss. So all the energy that is absorbed is really converted to heat. Only the energy that is reflected and transmitted travels, of course, furthermore in the air. But all other energy is converted to heat.
Let me extend that question. But this energy which is converted to heat is not enough to heat up your part.
Of course, yeah.
This temperature increase is non-significant, not significant.
Yeah, yeah.
Okay, so we wanted to keep it short and sweet. That's why we will take up all the other questions which have also arrived now at a later stage, and we'll contact you directly. And we will also prepare some sort of a frequently asked question section on our new website. So for getting more information, please visit our new website on Ultradur RX portfolio. You find it on plastics.basf.com. And in case you have sampling requests or direct projects you would like to discuss, please don't hesitate to contact me. You see my email address on the screen now. So again, many thanks for your attention. Many thanks for joining us. Take care and have a great day. Bye.